All right, AP, let's finish up Chapter 4 with our video lectures for sections 8, 9, and 10. Looking at our learning objectives, you're going to see some of the usual criminals. Translate among macroscopic observations of change, chemical equations, and particulate views. Again, that's understanding what's going on at the molecular level when you look at a chemical equation. Translate and observe chemical change into a balanced chemical equation and justify the choice of equation type, molecular ionic and net ionic, in terms of utility for the given circumstances. This is what we covered last PowerPoint presentation. Then relate the quantities, meaning the measured masses of substances, volumes of solutions, or volumes and pressures of gases, to identify stoichiometric relationships for a reaction, including situations involving limiting reactants and situations in which the reaction has not gone to completion. Again, basically saying be able to carry out stoichiometric calculations using things in solution. A little bit more specific for what we're doing in this presentation, classify a substance as an acid or base. It's going to be a little bit new in this presentation. Describe and identify strong and weak acids and strong and weak bases, and then apply stoichiometric principles to acid-base reactions. Again, acid-base reactions are the second of the three types of reactions that we're going to consider in this chapter. Here we go. Let's get started. Let's start with acid-base reactions, and this is according to the Bronsted-Lowry definition. There are more than one definition of an acid and base. There's more than one definition of acid and base. Typically, there are three different definitions that are useful for knowing. You've already looked at the Arrhenius definition. Here we're looking at the Bronsted-Lowry definition. According to the Bronsted-Lowry definition, an acid is something that donates a proton, basically an H+, right? That's just one proton. A base is something that accepts that proton. Okay, something that has a minus charge and is going to be strongly attracted to that H+. For a strong acid and base reaction, we look at something like H+ and OH-. One of the things that you're typically going to see at the end of an acid-base reaction is water. Okay, you're going to see water. H+, if that's a proton. Okay, something is a proton. OH, that is one of the easiest, strongest proton acceptors in the world, and this is about as simple of an acid-base reaction as you can get. So strong acids are strong electrolytes. Okay, remember our definition of what an electrolyte is, what makes a strong electrolyte? Something that completely dissociates in water. Okay, we see that light bulb light up nice and bright. So in water, if I take HCl, hydrochloric acid, it's a strong acid because it dissociates completely in water. In water, I'm going to get only H+ and Cl ions. There's going to be no formula units, no HCl in that solution, only the ions. But if I have a weak acid, those are weak electrolytes. So some of the dissolved molecules ionize, the rest remain as molecules. An example would be acetic acid. Okay, acetic acid is an acid because it does donate some protons. Some H+ go into solution, okay, but just a few, not all of them. So in that solution, I'm going to have, yes, a few H+, a few of these acetate anions, okay, the CH3COO- there, the acetate ion. But I'm also going to have in solution a lot of the acetic acid there, that whole molecule there, the CH3COOH. I'm going to have a lot of that still there. Some acids have more than one ionizable hydrogen atom. They ionize in steps. We're going to talk about that more in chapter 15. But for example, if you look at sulfuric acid, what we're going to have happen is one of those protons, one of those hydrogens are going to come off of the sulfate. And so you're going to get an HSO4 - 1. Because remember, sulfate has a -2 charge. If I only have one H+ to balance that out, I have an overall -1 charge. I've donated one proton. After that, that HSO4- is going to donate the second proton there. And so I will have donated 2 protons, and now I have a sulfate anion in solution. Let's look at strong and weak bases. If I have a strong base, most are ionic hydroxides. Okay, so main group 1, main group 2, even though some of the main group 2 hydroxides aren't very soluble, most of the things from main group 1, main group 2 hydroxides are going to be strong bases. A weak base, very much like a weak acid, means that it ionizes only partially. So I'm only going to throw a few OHs into solution. But here, the ionization process is different. Weak bases form OH minuses by accepting H pluses from water. So if I have ammonia, which is NH3, okay, if you remember it's a weak electrolyte, it's going to react with water to form some ammonium cations, NH4 plus, and some hydroxide anions, but not a whole bunch. There's still going to be plenty of ammonia in that solution. Another example, we have a methylamine. Here we go. Okay. As a result, we're seeing only a few OH minuses in solution. Most of the weak base remains in its molecular, nice and balanced form. Here we have a table that relates to the very common strong acids and strong bases. The best way for you to think about using this table is memorizing strong bases and strong acids. Just memorize strong bases and strong acids, and if you're working on a problem that does not identify that acid or base as strong and it's not in this list, you can go ahead and assume that it's a weak acid or a weak base.
Hydrochloric acid is a strong acid that completely dissociates to form H+ and chloride ion in solution. The H+ ion is rapidly solvated by water, forming the hydronium ion as shown. The hydronium ion reacts with the hydroxide ion from the dissociated strong-based sodium hydroxide to form water. In this neutralization reaction, sodium and chloride are spectator ions that do not participate in the reaction.
So when we go to perform calculations for acid-base reactions, first step, you have to list the species present in the combined solution before any reaction occurs. Okay, you have to have everything present in that reaction before it occurs. Then decide what reaction will occur, meaning how are you going to get some dissociation of protons, dissociation of hydroxide and ions. Secondly, write the balanced net ionic equation for this reaction. Again, balanced net ionic equation, meaning you're getting rid of all the spectator ions. That's going to allow you to identify the species that are participating in the reaction. And that's going to make it a little bit simpler for you when you go to calculate moles of the reactants, determining the limiting reactant, if it's appropriate, and then calculate the moles required for that reaction or product, and then convert to grams or moles or whatever as the question requires. What I want to do here is not harp on that you have to memorize this list. It should become a little bit second nature to you, but what I want to point out here is that the steps are pretty much the same as the steps that I gave you for the precipitation reaction. The idea is still the same. We're trying to put ourselves in a position where we can carry out stoichiometric calculations in a variety of situations. All we have to do here is list the species, identify them as strong acids, strong bases, weak bases, and that's going to inform our net ionic equation, which is going to be our balanced chemical equation for our stoichiometry. Now, when we're talking about acid-base reactions, one thing that is very common and needs to be talked about is a titration. It's the delivery of a measured volume of a solution of a known concentration, also known as the titrant, into a solution containing the substance being analyzed, the analyte. And so what I'm going to do is I'm going to take this substance that I don't know what it is. I don't know what the concentration of a particular substance is. I'm going to have a tall, skinny tube right on top of it, and I'm going to add drip by drip, milliliter by milliliter, something that I know exactly what the concentration is. And what I'm doing is I'm going to be measuring this unknown substance, the analyte, until it gets to its equivalent point. And the equivalence point is when enough titrant has been added to react exactly with the analyte. That means that I've gotten to the end point. The reason I know that I've gotten to the equivalence point or the end point is that an indicator that I've added to my solution doesn't participate in the reaction at all. It just has a color, and the color is the thing I can see. The indicator changes colors so that you can tell that the equivalence point has been reached. I know that I'm done. Having a look at that, here we have a tube I'm delivering to this unknown solution in the Erlenmeyer flask, just drop by drop. There's already been some indicator in the solution so that as I add drop by drop, a measured portion of acid solution, in this particular case, that the solution must be a base, is placed in the flask and an indicator is added. Then the base solution of a known concentration, I know exactly the concentration of whatever is in that burette, is slowly added. And I can tell you from the classes that I took at Chico State where we actually had to carry out these, you do it so painfully slowly, so that the moment that there's a color change, you immediately stop. And because these burettes right here have really nice, convenient volume measuring markings, you can know exactly what volume of that titrant was required to neutralize whatever was in that unknown solution. And since you know exactly what the volume was required, you can easily calculate the moles or the concentration of that unknown substance. So let's try on a concept check. Here I'll give you the answer for this, but please press pause so you can do this on your own, because here comes the response. What volume in milliliters of 0.2010 molar sodium hydroxide is required to neutralize 20.00 milliliters of 0.1030 molar hydrochloric acid in an acid-base titration? Here we go. We need to do 4 things in order to solve this problem. Now, in general, other titration problems can be solved in a very similar approach. So what you do here, the steps here, you can use in most titration problems. So step 1, I'm going to end up writing an equation describing the neutralization and obtain a stoichiometric factor relating moles of NaOH and moles of HCl. So I'm going to take this titrant that I have, the formula for the titrant. I'm going to add it to the formula of this this acid that I need to neutralize. I'm going to balance it stoichiometrically with the different coefficients, and I'm going to use that as I go forward. Once I determine how many moles of HCl are to be neutralized, I find the number of moles of NaOH required in that neutralization. Lastly, I determine the volume of the solution containing this number of moles of NaOH. Okay, so it's a very straightforward set of steps here. Let's move on to a concept check. I'll give you the answer here. Oh, sorry, this is the concept check. My bad. Here's the answer. I needed a separate slide because, well, a little bit of a long one. I want to show you some work here. Again, what am I doing here? Step 1, step 2, step 3, step 4. Step 1. First, write an equation for the neutralization reaction. Here we go. We have NaOH aqueous plus HCl aqueous react to form NaCl in the aqueous and then H2O liquid form. Okay. From this equation, we relate the amount of the titrant, the NaOH, to the given amount of the analyte, the HCl, and write the appropriate stoichiometric factor as a ratio. In this particular balanced equation, it's a 1-to-1. Makes it a little bit easy. It's not always this easy, but it is 1-to-1 in this particular example. Step 2. The number of moles of HCl to be titrated is the product of the volume in liters and the molarity of the HCl. So I want to know the moles of the solute. Okay, I can find out the moles of the solute by taking the volume of what I had and then multiplying that by the molarity of the thing that I know, right? Because I know this particular concentration. Because I know the concentration, I simply multiply the molarity by the volume. The volumes cancel out, and I have moles. 0.002060 moles of HCl. Step 3, now I'm going to use the stoichiometric factor to convert the moles of HCl to moles of NaOH that are required for that particular titration. And so I start with what I just got from step 2, the 0.002060 moles of HCl. I'm going to multiply that by the mole ratio that I got from my balanced chemical equation up top, the 1-to-1 ratio. What that allows me to do is go from talking about HCl to NaOH, which is what the question wants me to do. And so I have 0.002060 moles of NaOH. Step 4, we're going to use the inverse of the molarity of NaOH as a conversion factor. And the reason I know I'm going to use the inverse is because typically molarity is related as moles over liters. But here I want moles to cancel, so I'll simply invert because it's still equal to 1, right? Still equal to 1. I can flip them however I want. I'm going to use that as a conversion factor, the inverse of it as a conversion factor to find the volume of NaOH and convert that volume into milliliters. Why? Because the question wanted my answer in milliliters. And so what that looks like, so I'm going to take this moles of NaOH, multiply it by the conversion factor, the inverted conversion factor of the molarity. Okay, so that's, again, given to me by the problem, 0.2010 moles NaOH underneath 1 liter of NaOH. I have my 1,000 milliliters over liter conversion factor because, again, molarity deals in per liter, but this particular question wants it in milliliters. So a simple conversion will get me from liters to milliliters, and I have a final answer of 10.25 milliliters of NaOH. Here's another one I'll give you the answer. As in most stoichiometric calculations, we can combine these steps, okay? I'm sorry, I was mistaken. We're talking about the same thing here. Same problem, I should say, referring to what we just worked on. We want this milliliters of NaOH. Okay, we start with the volume, and again, it's in liters because that's what we're given of the the HCl to be titrated. We're then going to use molarity to convert the liters of HCl to moles of HCl. Because again, if I'm going to switch from talking about HCl to NaOH, I have to have a mole to mole ratio. If I'm going to have a mole to mole ratio, I need to be in moles. So once I get into moles of HCl, then I can use my mole to mole ratio. In this particular example, that is a 1-to-1. And then I'm going to invert the molarity of the NaOH here, just so that the moles of NaOH cancel, because that'll be the unit that I'm in right now. Then I'll have liters, a volume of NaOH, which again is what the question is asking me for, but it doesn't just want any old volume. It wants a volume in terms of milliliters of NaOH. And so I have one last conversion factor that converts liters of NaOH to milliliters of NaOH, and then I have my answer of 10.25 milliliters of NaOH. Let's check to see if this makes any darn sense. The molarity of the NaOH is just about twice that of the HCl. You know that because you read the question. And the combining the mole ratio of the acid and base, this suggests that the volume of the NaOH required should be just about 1/2 that of the HCl. And it is. 10.25 neutralizes about 20 milliliters of HCl. Now, here is a nice big old titration problem for you to try on your own, but I'm not going to give you the answer to this one in this particular PowerPoint presentation. You're going to have to check with your classmates or myself through a different avenue to double check your work. So, neutralization, we've already used this term. In the reaction of an acid with a base, the identifying characteristics of each cancel out. You have proton acceptor, you have proton donator. Yes, the proton has been donated and accepted. So neutralization is typically we're talking about the complete. Okay, neutralization is complete reaction of an acid with a base. The products of this neutralization are water, H2O, in the liquid state, and a salt. Again, there's just another name for an ionic compound, something from the left side of the periodic table and something from the right side of the periodic table. So here is a concept check with an answer. I'll give you the answer to this. So go ahead and try it on your own so you can double check your work. For the titration of sulfuric acid, which is H2SO4, with sodium hydroxide, NaOH, how many moles of sodium hydroxide would be required to react with 1.00 liters of 0.500 molar sulfuric acid to reach the end point, the equivalence point? Go and press pause because here comes the response. It ends up being 1.00 moles of NaOH. The balanced equation here is H2SO4 plus 2 NaOH react to form 2 H2Os and then Na2SO4. 0.500 moles of sulfuric acid is present to start. Due to the 1:2 ratio in the equation, right, the mole ratio, 1 mole of NaOH would be required to react exactly with that sulfuric acid. So 1 mole of sodium hydroxide would be required. So here's some concept checks for you to try. I'm not going to give you the answer on this PowerPoint presentation. You're going to need to check with your classmates or myself through some other avenue to check your work. So, big ideas here. Where are we going? We're trying to find the moles of NaOH required for the reaction. How do we get there? What are the ions present in the combined solution? And what is the reaction? What is the balanced net ionic equation for that reaction? So once we have the balanced net ionic equation for the reaction, we know what species are reacting, and we know how many moles of each are required. And then what are the moles of H plus present in the solution? Lastly, how much HO minus hydroxide is required to react with all of the H plus present? Moving on to section 9, oxidation reduction reactions, aka redox reactions. You've heard this one before. Translate an observed chemical change into a balanced chemical equation and justify the choice of equation type, molecular ionic or net ionic, in terms of the utility for the given circumstances. A little bit specific for section 9, I want you to assign the oxidation numbers to elements in compounds or ions. I want you to recognize a redox reaction and then determine whether the equation for the reaction is balanced. Lastly, define and recognize oxidizing and reducing agents. Those are going to be two new ideas in this presentation. Oxidation is simply the loss of electrons. The opposite of that is reduction, which is the gain of electrons. Both oxidation and reduction must occur simultaneously. You can't have something lose electrons unless something is gaining electrons. You can't have something gain electrons unless something is losing electrons. Historically, oxidation used to mean combines with oxygen. That's why it has that base oxy, because that's how it was first studied before the actual transfer of electrons was actually understood or even known to exist. The modern definition is much more general, the loss of electrons, gain of electrons. Moving on to oxidation numbers. An oxidation number is the charge of an ion or a hypothetical charge assigned to an atom in a molecule or a polyatomic ion. And we say a hypothetical charge because an atom in a molecule does not have a charge. If it's in a molecule, that means it's covalently bonded. If it's covalently bonded, that means you're simply filling up the valence shell electrons. You're not forming an ion at all. An example, in NaCl, the oxidation number of sodium is +1. The oxidation number of chloride is -1. Is the actual charge, right? That's simple. In an ionic compound, it's the actual charge. In CO2, however, it's a molecular compound. There are no ions, just covalent bonds. The oxidation number of oxygen is -2 because oxygen as an ion would be expected to have a -2 charge. The carbon in CO2 has an oxidation number of +4. But let's ask, why? Because there are 2 oxygen atoms that are very strongly attracting, each of them, 2 electrons. And so if you have 2 oxygen atoms strongly attracting 2 electrons each, you're strongly attracting overall 4 electrons. Where are they attracting the electrons from? Carbon. How do we identify that carbon is having those electrons drawn away from the carbon? A +4. So here are some general rules for assigning oxidation numbers. These are going to be very similar to the things that you read about in general chemistry. We're just going over them again. Number 1, for the atoms in a neutral species, an isolated atom or a molecule or formula unit, the sum of all the oxidation numbers must be 0. Okay, very similar to our idea of ionic charges, but here we're talking about oxidation numbers. For the atoms in an ion, the sum of the oxidation numbers are equal to the charge of the ion. Okay, so if it's a molecule or a formula unit, the sum has to be 0. But if there's an ion, meaning there is an overall charge, whether it's plus or minus, the sum of the oxidation numbers have to be equal to that charge. In compounds, main group 1 metals all have oxidation numbers of +1, and main group 2 metals all have oxidation numbers of +2. It's very easy. They're donating, or they're allowing however many valence electrons they have to be drawn away from them. They have respectively 1 and 2 valence electrons. In compounds, the oxidation number of fluorine is always -1 because it's the number 1 most electronegative atom on the periodic table. So it always gets what it wants, and it wants 1 electron, so a -1 oxidation number. In compounds, hydrogen very commonly has an oxidation number of +1. The only exception to that is if it acts as an anion, it would be called hydride, and it's going to have an oxidation number of -1. In compounds, oxygen most commonly has an oxidation number of -2. Unless it is in a peroxide, then it's going to have an oxidation number of -1. The other exception being if it's bonded with fluorine, in which case, if it's bonded with fluorine, it's actually going to have an oxidation number of +2. And lastly, in binary compounds with metals, main group 7, okay, the halogen elements have an oxidation number of -1. Main group 6 elements have an oxidation number of -2, and main group 5 elements have an oxidation number of -3 for the most part. There are some exceptions, but for the most part, these are pretty steadfast. So let's go through a concept check. I'll give you the answer here so you can check your work. What are the oxidation numbers assigned to the atoms of each element in KClO4 and Cr2O7-2? Go ahead and press pause because here come the answers. The oxidation number of potassium is +1, according to Rule 3. The oxidation number of oxygen is -2. And the total of 4 oxygen atoms is -8. For these two elements, the total is -7. The oxidation number of chlorine in this compound must be +7 to give a total of 0 for all atoms in the formula unit, as per the first rule. The oxidation number of oxygen is -2. Again, as per Rule 6, the total of the 7 oxygen atoms is -14. The total of the oxidation numbers in this ion must be -2. Therefore, the total of the oxidation numbers of the 2 chromium atoms is +12. And that of 1 chromium atom must be +6. Here's an opportunity for you to try this on your own. I will not give you the answers on this PowerPoint presentation. You're going to have to check with your classmates or myself through a different avenue in order to check your work. One of the other objectives was identifying an oxidation reduction reaction. In a redox reaction, the oxidation number of a species changes during a reaction. Oxidation occurs when the oxidation number increases, meaning you're losing electrons. You have a more positive number. Reduction occurs when the oxidation number decreases, meaning that species is gaining electrons. You're becoming more negative. If any species is oxidized or reduced in a reaction, that reaction is a redox reaction. So, examples of redox reactions: any displacement of an element by another element, combustion, for example, or the incorporation of an element into a compound. So if we look at the particulate view of a redox reaction, for example, magnesium plus a copper 2 ion reacting to form magnesium ion and copper. Okay, just copper. Notice that before the reaction occurs, copper is the ion, and after the reaction occurs, magnesium is the ion. That is key here, because electrons are being transferred from the magnesium metal to the copper 2. Because we have a +2, that means we're 2 electrons short. 2 electrons are being transferred from the magnesium to the copper, and the products are therefore copper, completely balanced, but because magnesium gave up 2 electrons, it now has a +2 charge. Redox reactions must balance according to both mass and electric charge. A complete method for balancing such equations will be represented in Chapter 18. We probably won't get quite that far. But for now, our main goals will be to identify oxidation reduction reactions, balance certain simple redox equations by inspection, meaning balance, and then recognize in all cases whether a redox equation is properly balanced. So, an oxidizing agent causes another substance to be oxidized. Okay, it's the agent that does the oxidizing. It causes something to be oxidized. The oxidizing agent itself is reduced. A reducing agent causes another substance to be reduced, but the reducing agent itself is oxidized. In the example of that we've already looked at, magnesium plus copper 2, what is the oxidizing agent? What is the reducing agent? Go back to your definitions of what it means to be oxidized, what it means to be reduced. So the maximum oxidation number for a nonmetal is equal to the group number. For example, for nitrogen, maximum plus 5. For sulfur, maximum plus 6. For chlorine, maximum plus 7. The minimum oxidation number is always going to be equal to the group number minus 8. All right, let's finish up with section 10. You're going to design or interpret the results of an experiment involving a redox titration, and then recognize a redox reaction and determine whether the equation for the reaction is balanced, and then balance redox reactions. So when we balance redox reactions, we're going to be using the oxidation states. So start. Again, this is going to look somewhat familiar. Most of these steps are going to be familiar. Write the unbalanced equation, then determine the oxidation states of all atoms in the reactants and the products, and then show electron gained or lost using what we call tie lines, meaning draw a line between two versions of an element, one on the reactant side, one on the product side, in which the oxidation states are changing. That means you're either gaining electrons or losing electrons. Right now, doesn't quite matter, but you're showing that there's electron lost or gained. Then use the coefficients to equalize the electrons gained and lost. And that's what we mean earlier in the presentation by you're going to have to balance, show conservation of atoms as well as conservation of electrons. Balance the rest of the equation by inspection is regular old balancing. And then lastly, you can add your appropriate states. When we balance the reaction between solid zinc and aqueous hydrochloric acid to produce aqueous zinc 2 chloride and hydrogen gas, let's ask ourselves, what is the unbalanced equation? We haven't balanced this at all, but again, we have solid zinc and aqueous hydrochloric acid, right? On the product side, you're going to have aqueous zinc 2 chloride, representing these here as individual ions, and hydrogen gas. Next, what are the oxidation states for each atom? I have zinc solid. Okay, it's isolated by itself, just going to be 0. The hydrogen hydrochloric acid is a +1. The chloride there is a -1. On the right side of the reaction arrow, that zinc ion is going to have an oxidation number similar to its charge, so +2. The chloride ion, oxidation number of +1. And that isolated hydrogen, which is pure hydrogen, that is going to be a 0 oxidation number. 3, how are the electrons gained and lost? And so we're looking at what we just did here. I have the same equation with the oxidation numbers. I'm noticing that one electron is being gained twice. Okay, one electron is being gained twice. And so that hydrogen on the left side of the reaction arrow had a +1 oxidation state, but on the right side it was 0. So I'm going to need to gain 1 electron to make that happen. But there are 2 hydrogen atoms there, so it's happening twice. So that means that there are going to be 2 electrons lost. So where does that happen? Oh yeah, the zinc. From the zinc solid to the zinc +2, that's where the 2 electrons are being lost from. The oxidation state of the chlorine remains unchanged. The movement of these electrons is called a half reaction. So if you look at the gaining of electrons, that's a half reaction. The losing of electrons is a half reaction. Number 4, what coefficients are needed to equalize the electrons gained and lost? Again, balancing the number of electrons. So again, I have 1 electron gained by each hydrogen. That hydrogen over there on the left is not being pointed at. It should be pointed more towards the chlorine. And we have 2 electrons being lost by the zinc. In order to balance that, I'm simply going to put a coefficient of 2 in front of the HCl on the reactant side. And I end up having conservation of electrons on both sides of the reaction. Number 5, what coefficients are needed to balance the remaining elements? Right? I just put a 2 in front of the hydrochloric acid in order to balance the number of electrons. But now I need to balance the number of atoms, right? And that's going to require me to put a 2 in front of the chloride. With that, we finished chapter 4. I know it's a lot of new stuff, but I have a concept checked for you with no answer. This is going to make you use everything that we've gone over so far in chapter 4. Sodium nitrate is used in the production of fabric dyes. Who cares? As a meat preservative. I like meat, but who cares? As bleach for fibers and in photography. It is prepared by passing nitrogen monoxide gas and oxygen gas into an aqueous solution of sodium carbonate. Here, you're getting the idea. We're going to have to write a balanced equation. Carbon dioxide gas is the other product of the reaction. So A, write a balanced equation for that reaction. B, what mass of sodium nitrite should be produced in the reaction of 748 grams of sodium carbonate with the other reactants in excess. And C, in another preparation, the reactants are 225 milliliters of 1.50 molar sodium carbonate, 22.1 grams of nitrogen monoxide, and excess oxygen. What mass of sodium nitrate should be produced if the reaction has a yield of 95.1%? That's going to take you quite a while. I'm not going to give you the answer in this particular presentation. You're going to need to check with your classmates or myself in another avenue to double check your work. But that ends this chapter.